Let's solve the centuries-old mystery of one-way speed of light. Derek Miller from YouTube channel Veritasium has already prepared an excellent video on why we only know an average of two-way speed of light and why we have not been able to measure the speed of light in one direction. In this video, we'll create a mechanism to measure the one-way speed of light. Derek himself has suggested one method which he later discarded, but I feel with minor tweaking that can also work. Before we move ahead, I would like to thank Derek again for his video, without which I would have never known that this problem ever existed. The prior experiments utilized a mirror kept at a distance and they measured the time taken by a light beam to reach to that particular mirror and return back. They estimated the speed of light by dividing the distance, which was already known by the time they estimated. These experiments utilized some kind of rotational mirror or some kind of light blocking mechanism to estimate the speed of light. The idea was to ascertain the speed of light by using the rotational speed of mirror or cogwheel. If these were not rotating at the correct speed, the light would not be visible to an end observer. In all these cases, the speed of the light which was observed or measured was two-way. But why, even after so many technological advancements, we have not been able to measure the one-way speed of light? This actually requires two synchronized clocks, which can be synchronized if they are kept near to each other. But once they are moved, due to their relative motions, it cannot be certainly said if they are in synchronization or they have changed. Now, what we can do is that we can send a beam to resynchronize the clocks, but we do not know how much time the beam is going to take, because this is the same thing which we are going to measure. If we see, the entire system is based on the digital computers, but the digital computers in turn are based upon the average speed of light. So a simple solution could have been a mechanical computer or an analog computer to solve this issue. And if we see, all of the previous experiments also utilized a similar mechanism. Now, with the advancement in the technology, we can expect to have higher precision components which can give us more accurate results of the one-way speed of light. In this video, we'll discuss 5 different methods to measure the speed of light in one direction. The method 1 is based upon a phenomenon of a light ray created by a strong light beam. A strong light beam illuminates particle falling in its path, thus making the light ray visible from miles away. In this method, we'll measure the length of the beam, which would depend on the length or duration a high-speed shutter remains open and the speed of light in that particular direction. We can create a high-speed mechanical shutter using a rotating cylinder at 1000 rotations per second with a slit of 1 mm and with a circumference of 100 centimeters, thus making a mechanical shutter of 1 microsecond, which is 1 millionth of a second. Assuming the speed of light is 300,000 kilometers per second or 3 lakh kilometers per second, during 1 microsecond, light travels approximately 300 meters. Therefore, our shutter would create a light beam of 300 meters, which we can capture through a high-speed camera kept perpendicular from this beam. If the length of the beam is longer, that means that speed of light in that direction is faster, and if it's shorter, that we would be able to conclude that the speed of light in that direction is slower. Now, there are some limitations of the method 1, such as that it can only work in the night or dark time. It can't be used in vacuum because there won't be any particles which can be illuminated if they are coming in the path of the beam. It may also be possible that high-speed camera sensor is not sensitive enough to register the length of the beam, because many high-speed camera systems utilize special type of lighting setups. In such case, the method 2 will eliminate such limitations. In this, rather depending on the particles to illuminate and show us the length of the beam, we would place some diffusers in the path of beam and we'll create multiple parallel beams originating from the same source in parallel at the same time. If the beam is hitting to any diffuser, the same will get illuminated, similar to the particles in the method 1. And if the beam continues to hit it, or it's still passing through the diffuser, the same will remain illuminated. But in case where the light has not reached to the diffuser or it has already passed it, the diffuser won't be visible. So by taking a snapshot from a high-speed camera, we can see which is the nearest or farthest diffuser illuminated by the light beam, and thus can estimate the length of the light beam. Now, this will have another flavor to it, in which we can utilize two different frames and compare the different diffusers illuminated by the light beam, and the time would already be known because we would be knowing the time difference between two frames. This particular method has a limitation in which we actually see that the light is traveling in two different directions. First, in the direction which is depicted by the red, which was the original direction of the light beam. Second is depicted by the green, originating from the different diffusers to reach to the camera sensor. But the same can also be resolved by placing the camera in the opposite direction in the mirror arrangement. Now, because of this, both setups would look like this. And if we see, by placing the two cameras in this particular system, the green portion will cancel it out because the light beams are in opposite direction. And by taking the average of the setup 1 or setup 2 from the flavor 2, we should be able to estimate the speed of light in one direction. Direct system was also on the similar lines. By placing this same or the another camera in the mirror position, and then by taking the average of the both setups, we can estimate the speed of light in one direction. The third method utilizes the feature of light in as per which the light travels slower in glass or water than air. So we'll send two beams here, one through air, another through the glass fiber. If we know that when the beam are reaching to a receiver and what is the difference between both of those, then if we know their relative speed, then we should be able to calculate the speed of light in that particular direction. In order to calculate that, we'll send two beams. The red one depicts through air and the yellow one through glass fiber, and these will reach to a specially designed receiver at different times and will mark their hit point depicted with red and yellow dots. Now this receiver would be in the similar lines of the initial high speed shutter, would have 1 millimeter sensors spread across its entire 100 centimeter circumference, and it's expected to rotate at 1000 rotations per second. The total number of sensors thus would be 1000 spread across the entire circumference. Now we already know that there is a refractive index of glass, which is actually based upon the principle that whatever the speed of light is in that particular direction, it is always going to carry that same 1.5 ratio between the speed of light in air and the glass. Now utilizing this same principle, since we would be knowing the distance between source where the beam originating from and the receiver where they are hitting, and the speed of rotation of the receiver, and the different sensors where the light beams coming through air and glass fiber are hitting, we should be able to calculate the speed of light in that particular direction using the refractive index, which is 1.5 approximately for glass. Now in method 4, we'll utilize similar type of mechanism as we discussed earlier for source and receiver. The only catch here would be that both source and receiver would be rotating at the same RPM, and for a change, we'll keep them nearest as possible. Since both of these are rotating at the same RPM, the originating beam from source, which would be originating 1000 times per second, would be hitting the same sensor at the receiver, depicted with the red place. Now, what we'll do in order to measure the speed of light, we'll move it away 300 meters or more, and thus it should hit the next sensor, because we are already aware of that difference between two sensors at this particular rotational speed is 1 microsecond. And if the speed of light is 300,000 km per second or 3 lakh km per second in that given direction, Just after 300 meters or so, we should be able to see that the beam start hitting the next sensor because the distance would be increased by 300 or more. And going forward, by utilizing different distances, we can again measure the speed of light with an accuracy of 3 to 400 meters per second. If it's slower, then we would need to travel a little more distance in order to see a shift to another sensor. And if it's faster, we should see a shift to from the initial sensor to second sensor within the 300 meters range. Now, this is my favorite method, and it's expected to be most precise, even up to a range of 40 to 50 meters. Here, similar to the method 4, we'll be utilizing a source and a receiver rotating at the same speed of 1000 rotations per second and with similar features such as 100 centimeters circumference. Now, rather having receiver studded with sensors, for more precision, we'll be utilizing a specially designed disc. Let's call it a Raghavendra disc, which will be having 1000 different facets at the place of 1000 sensors we saw in the method 4. These facets of Raghavendra disk would be having different angles in yaw and pitch directions, and it would look something like this. As we can see here, in yaw and pitch directions having different angles would be able to reflect the light beam approaching it in different directions, which means when we are having different directions or different angles for different facets, light beam hitting those will not hit the same spot after getting reflected, and every facet would direct the light in the different direction. Now, if we have 20 pitch angles and 50 different yaw angles, by multiplying those, we get 1000 unique angles, one for each of the facet of the Raghavendra disc. But since we are using reflectors here, aren't we measuring the light in two different directions? Well, actually, no, because the fate of light is getting frozen at the time it is hitting the reflector. The purpose of reflector is just to direct light in different direction. And since we are not measuring the time, it does not affect it. But it would only depend on the distance between the Raghavendra disk and the origin of the light beam. So how it is supposed to work? So the source and receiver Raghavendra disk will be kept closest as possible. Both would be rotating at the 1000 rotations per second. And once the beam approaches it, it will again continuously approach the same facet of the Raghavendra disk, similar to which we saw in the method 4. The concerned reflector will start reflecting it to a dome which is painted with afterglow material or some other screen which can make the light visible where the beam is hitting. Now, this process would happen 1000 times a second. Once we move or change the distance between the source and Raghavendra disk, this impression, which will be in the shape of a line segment on the dome, would also shift. Now, since it's an analogous or computer type of thing, it's going to be a continuous shift and not a sudden shift for that particular facet too. Now, there is a possibility that the light beam may be hitting two different segments, but again, this will also be a gradual shift. Assuming where we have a dome in semicircle shape with a radius of 1 meter, then the length of the impression created by the light beam would be about 1 centimeter long. The beauty of this method is that if we change the size of dome without changing any other element or component of this entire method, we can increase or decrease the precision. Now, rather having a dome with 1 meter radius, if we utilize a dome with 10-meter radius, assuming a dome with 1 meter radius has an impression of 6.28 mm, then a dome with 10-meter radius would have an impression of 62.8 mm, or simply 6.28 centimeter. Now, by looking at the shift in the impression on the dome resulting from a shift between the distances between source and Raghavendra disk, we can estimate the speed of light in that particular direction even up to sub 40-50 meters accuracy. Thank you.